All right, welcome back. Let's do some classification now. So classification is basically where we want to create a model that can distinguish between two or more classes in a data set. So here what we need to pay attention to is the fact that the class, when we do classification, the outcome variable should be categorical, right? So, um, so we were doing regression for numeric type of outcomes where the output variable was a numeric continuous value. For this one, the outcome should be a categorical type. So the dataset that we want to work on today is the Pima Indians diabetes dataset. So you see here it specifies the target type as categorical. So that means this is a good candidate dataset for for classification purposes. Double click on it, make sure this is green. If it is green, it means it's there. It's loaded. So let's see how it looks like. So you see the first column there, it's called outcome, and that's showing diabetic or non-diabetic values. So that's the outcome variable, the output variable, the target variable. And there's different measurements taken from these people. So each row is a person here, right? Pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, and the age of the person are the measurements taken. So these are the attributes. So the model is going to learn from this data set. And then when a new data point comes in, meaning in this case a data point refers to a patient, right? A person coming in, and then they will measure all these attributes on that person, and then this model will be able to determine, say, whether that person has diabetes or not. That's the purpose of classification. So, yeah, a few other things here that we can use is, for example, this feature statistics could be quite useful to get a quick view of how the data looks like. The blue and red are for the two classes we have, non-diabetic versus diabetic. You can also see a quick distribution of how many points are in each class, right? This is for the outcome, so this is a bar chart. The others are numeric values, so these are histograms. So this one, yeah, there's a few more. It seems like actually almost like the same, like twice, right? Basically, the blue values, the non-diabetic patients or people are two times the diabetic people there. Okay. So that's a quick view of the data. The data info could be useful in this regard as well, just to get a, you know, uh, brief overview of seeing how many rows there are, how many columns there are, how many numeric and categorical columns we have, and the output variable type. Okay then. So now let's start with a model for our classification purpose. So you need to pay attention here. Some of the models are good for only regression, some are good only for classification, and some can be used for both. Linear regression is a regression model that said you cannot do classification with this. This logistic regression, although the name has regression in it, it's very misleading there. You should not pay attention to that. This is a classification model only. Okay, it's basically, they are very related though. So this logistic regression model applies a logistic function or a logit function on the kind of the linear function we have. So that's where maybe the name comes from as well. I'm not sure about that. But basically both of these come from the statistic field. Um, that's where they come from. And now, they are definitely used a lot in data mining or the machine learning areas as well. So decision trees can be used for both. Random forest gradient boosting is at the end a collection of trees, so they can be used for both purposes. KNN for both purposes. Naive Bayes should be available only for classification, and there's a few models here as well. So yeah, there's quite a few models we can try. We will start with a logistic regression function, which is one of the easier models to work with. So we dragged logistic regression here. What we'll do, we will connect this to test and score, right? And what we need to do is also connect this data to the test and score. So you see we have the data coming from this upper side, the model is coming from here. And over here, if you double click now, We will see cross-validation, or we can apply these other techniques as well. I'm going with cross-validation with tenfold. I will apply stratified sampling. So what does stratified sampling do? When these folds are created, right, the points are randomly assigned in each one of them. But what stratified sampling will do, it will track of the ratio that is present in the initial data set of the blue and red class of the basically in this case diabetes versus non-diabetes class. So this ratio will be preserved in each of the folds. So this is roughly about 66%. Yeah, I think this value here, 6.64, that basically non-diabetic patients is about 64% of the data and 36% of the data is diabetic, right? This is the ratio in the main data set. So this 64 to 36 ratio will be preserved in each of the folds when we do cross-validation, okay? Or when we do random sampling here, we could do that as well. For example, we have set, let me change this so that it will be easier to understand. Okay, let's make it 80%. So here, each time it will create a out of the 80% of the data, it will create a training set, and then the 20% will go into testing. But in that training set and the testing set, this ratio will still be preserved, this ratio, 64 to 36 ratio, this one of non-diabetes versus diabetes class will be preserved in each one of them, okay? And the same thing for these cross-validation folds as well, they will be preserved. Now, what's the importance of this, you might wonder? Well, because if it was just randomly assigned without tracking the class ratios, right? For example, if you go with just this fold example, cross-validation example, one of the folds can be 10% of diabetes and then 90% non-diabetes, whereas the other fold could be 40% diabetes versus 60% non-diabetes. Another fold could be just 1% diabetes versus 99% diabetes. Now you might think that's almost impossible. Still, it is possible, right? I mean, it is very low that will happen with 1% and 99% there, but it can happen because it's randomly assigned at the end. Now I'm kind of exaggerating there a bit, I know, but the main thing here is that you need to consider that we really want to preserve that ratio that we have at the initial data set. This also makes sure that each training fold and testing fold at the end will have the same ratio, so at least we are not, tinkering with that end. So when we get different results, at least we'll know that the ratios were preserved, so we didn't change anything there that will impact the model performance. Same idea for random sampling too, right? So this is not maybe that, I mean, in regression, we can't really talk about stratification, but in classification, stratification is important. So please make sure that you select stratified here, either in cross-validation or this random sampling. All right. Okay. And now with that aside, we need to talk about this too. So these are the metrics, the performance metrics of a classification model. CA is the most common one. It's for classification accuracy. It's basically out of all the predictions it made, how many of them were accurate. Okay. Meaning how many of the points were correctly identified as their true class. Whether it's diabetes or non-diabetes, were we able to identify them correctly? That's it. Now, the more important ones are these F1 precision recall. So I want to briefly talk about those. Okay, so let me open this. So what is, well, first of all, let's do this. Before we start talking about these, we need to talk about something more, and that's this one. So here, first of all, let me show this predictions. Okay. So what do we have here? We have the actual output variable. We have the prediction from the logistic regression. So here you see this. The person has diabetes. Model says they have diabetes, so that's good. So that's a match there. That's correct. This is a non-match, a misalignment there. You see diabetes is the actual case, and the model says, okay, this person does not have diabetes. So that's wrong. So there's a misclassification. So this is an error. Or the other way. So this one is also an error where, for example, the person does not have diabetes. Yeah, this one, it's non-diabetic, but the model predicts the person to be diabetic. That's also an error, misalignment. You see, basically that's a misclassification there. But when we have like this one, they're matching, or this one, they're matching whether diabetes or non-diabetes, that's a good thing. That's what we want the model to do as much as possible. That's accuracy. That's the classification accuracy. Just a quick note, logistic regression makes predictions in terms of probabilities. So it predicts, in this first case, the point, that data point, that person to be non-diabetic, 0.11. That's the probability there. And it predicts the person to have diabetes, to be diabetic, 0.88. The probability value there is 0.88. Okay, so that's the, and basically it will go with the larger probability. So that's, since the diabetic probability is much larger, the prediction will be, okay, this person has diabetes, so that's the final label, predicted label here. That's how the prediction goes there. Okay, so now let's look at another important topic, which is the confusion matrix in classification. So what do we have here? Well, what we are looking at is what we call this confusion matrix. So basically it means how confused is matrix. So it will make mispredictions, right? Classifications. So that's what we refer as confusions. Now, how confused it is. So basically it's a class level, kind of more detailed look at the errors being made. So here, okay, so here, what do we see? So inside there's the probability values, but let me change that. Yeah, this is easier. I want to see the numbers. Looking at just the numbers, it's easier. So basically these numbers you see is the number of data points. On the rows, we have the actual labels. On the columns, we have the predicted labels. Predicted labels are coming from the model. So what does this mean? For example, this row is all the actual people who do not have diabetes, right? There's 500 in total. And this bottom row is where people have diabetes. There's 268 of them. Okay. Now, when you look at the prediction columns, the model predicted 554 people to have no diabetes and 214 to have diabetes. That's the prediction column there. Now, when we look at the intersection, so this part is basically a good prediction because it's correctly identified, right? Those people who do not have diabetes from the row, that's the actual. When you look at the column, that's the predicted label. So they match with each other. So there's 437 correctly identified non-diabetes people, and there's 151 correctly identified diabetic people by the model, because you see this row over here, this is the people who have diabetes, and the predicted column says, okay, they have diabetes. There's 151 of them. So that's good. So these two, basically, if you add them up, will define the accuracy of the model. The classification accuracy is this, the total of these two divided by the total of all the points we have, which is 768. All right. This diagonal is the error diagonal, basically. This is the misclassifications. Okay, so if you add this up and divide by 768, you will get the error of the model, classification error, misclassification error. Those are the names being used, so that's the error of the model, classification error. So what do these do? Well, these people, 63, they do not have diabetes, you see, but they were identified as to having diabetes by the model, so that's wrong. And here 117 people do have diabetes, but the model said no, they don't. So there's 117 of them. So that's also wrong. Now, because there's people over here, so generally, by the way, we also always kind of identify a group as positive and the other group as negative. Here, we'll identify the diabetic group as positive class, positive group, and the non-diabetic class as the negative class. Okay, so if this is the positive class, and by the way, you can do other way as well. It's up to you. Generally, the positive class is really what you want to identify. And I think based on this data, the goal is to identify whether a person has diabetes, right? So that's why I went with, this diabetic class being the positive class. That's it. So here, the model is saying these diabetic people who have, who are actually positive, they do not have it. So it falsely claims them to be negative class. So that's why this is referred as false negative right here in this 117 cell. In this cell, the model, there are 63 patients who do not have diabetes, but the model claims them to have diabetes. So this is, it falsely claims them to be positive. So that's why this is the false positive cell, this 63. So you see this is a false positive, this is false negative, so these two are the misclassifications. All right. And of course, this is based on this definition. This is a true negative, the 437, and 151 is the true positive because they were correctly identified, so they are true. This is the positive class, so true positive, and this is the true negative, this 437. Okay? Okay, so now I hope that was understood. This is pretty important. Confusion matrix itself is very important. Can see in detail how good the model is doing in each class. Okay, it's very important. And also, just a quick note here, so that you can understand the significance of this more. So we have 117 error here, 63 error here, without paying attention to the size of this numbers. So I'm not paying attention to how large or how small they are. But basically, if I want to improve this model, I will need to decrease this 63 and 117, right? So that the model will have less error then. Now, if I were to try to do that, and if I had a chance to focus on one of the things more than the other one, which one do you think is more important here? Is 117, decreasing the number 117 more important, or decreasing 63 more important? Or stated other way, which one poses more risk, poses more importance? It's basically a more bigger danger to the patients. Think of it that way, and kind of consider this data. We are identifying whether a person has diabetes or not. So if you think about it, this one, right here, the people have actually they are diabetic. They are actually in reality, I mean, in real they have this diabetes, right? The actual label is diabetes. The model is saying no, you don't have. So what will happen? Well, these 117 people, they will happily be sent home. The doctors are happy. Those patients are happy. They go home, and then maybe after a few months, after a few years, they get more sick. They get more ill. So the situation worsens, right? Think about it, and then maybe it gets to a situation where it cannot be even healed anymore. I don't know what the situations might arise after this, but basically it will be worse than it is now. So then they will come back, and then they will be in a much worse condition. Okay. That's the importance of 117. Now, what about this one? So basically, what I'm saying right now is this one is more important, right? So we need to decrease this number more the goal of this study, of this research, or of this model would be, I should be able to find all those people who have diabetes. That's the main goal here, really. Now, what about this one? The 63 people, for example, they did not have diabetes, as you see, but they were identified as being diabetic. Now, yes, they got sad, they got anxious, and etc. They maybe had to go through more tests, more examinations, etc. But probably there's more advanced tests after this, maybe more studies, more things to do, whatever they do, and then they will be identified as, hey, okay, at first we thought you have it, but no, actually you don't have it, so you're good, right? Basically, maybe it's a more costly process they will go through, kind of. Okay, it will be more costly both maybe for them and maybe for the hospital and different resources as well. But at the end, it's important that, okay, they were identified as not having diabetic after more tests, right? So that's not too important, but this one is important, right? Because this has real risk to it. Because if you send those people home without, when you say, okay, you're good based on a model, and actually they're not good. So now you're making everything much worse then. So basically the cost of this one later on probably will be much larger, both to the society, those people, to the hospital, to these, what's it called, the health insurance in general. Everything will be more costlier in this one actually, if you were to really even look at the costs associated with these errors here. Okay, that's an important side note, but I just wanted to mention here, kind of to understand this topic better. So when we do classification, we are not just kind of depending on the situation, right? This is an important thing. Maybe let's say this model is being used as a helper aid to a doctor. So, just maybe the system designed this or whatever they went with this, where they don't just go with the doctor's decisions, but also take into account the model's input. And maybe model's input is being, relied on quite a bit. So right now, this model, I wouldn't really rely on it as is because it's not doing super good. But, you get the idea. Okay. All right. Now that's important. So from these values, we can basically these F1 precision recall are calculated. Okay. Now I'm not really going to go into the like formulas of those models. Basically, they make use of these false positives, true positives, false negatives, all these things. They make use of that. But instead of giving you the formulas, I will try to explain what they are. So recall, what does it do? Recall basically says this: out of all the positive data points in my data set, how many of them are correctly identified as positive by the model? Okay, so there's positive data points. How many of them are correctly found by the model? Okay, where is the positive data points? That's this row here. You see, these are actual positive data points. There's 268 of them. How many of them are correctly identified? Well, 151 of them are correctly identified by the model. Right? So this is the prediction column, and this is the actual, so that's 151. So 151 divided by 268, that should give you, and actually I will just select this one here, diabetic. That's recall 0.563, right? Is about half, about 50% of it. Now, why did I select diabetic here, by the way? So when you say diabetic here, you're telling this orange here that the diabetic class is the positive class. So these calculations, F1 percentage recall, is done at the class level. Okay, classification accuracy, AUC, MCC, these are at the general model level, so it's aggregate level, so they don't change anything. But here, you identify which class is positive. So you can say non-diabetic is positive as well. So you see the calculations will change based on that. So when the focus is on the non-diabetic class, you see the model is doing much better. But when the focus is on diabetic, so when you take the diabetic class as positive, right? That positive basically will determine where is the true positive, where is the false positives, all those values. So based on your positive class, those values will change. That's why these calculations change as well. And you see the diabetic class, which is more important for us to identify, has a much lower performance, especially in recall, which is more important for us because the recall is saying out of all the positive patients, meaning out of all those people who have this disease, how many of them are found correctly? What percentage or the ratio basically? 0.56, so that's 56% was found correctly. So that's, you see, this one basically. So we need to decrease this one as much as possible. So that means we need to increase this 151. So basically we need to make a shift from this 117 into 151. Okay, that's the goal here. So recall is pretty low. So this model really is not good to do anything with. All right. Now classification accuracy doesn't look too bad, but then really my focus would be on recall in this data set really. Would be on recall. Okay. No, so that's recall. So what does precision say? Precision says, out of all the possible predictions made by the model, how many of them are correct? So you see, this one focuses on this column because this is where we make positive predictions, right? Where the model makes positive predictions. Then how many of them are correct? Meaning how many of them are actually positive? So out of this 214 data points, 151 are correct. So the precision calculation is 151 divided by 214. Okay. So this is also important because we really want this precision to be high as well, so 0.7. But then, if our goal is to find all those patients, right, this row who have the diabetic, who are diabetic, this row basically, then that means if you want higher recall, the precision will go down. So generally, precision and recall are kind of in a balance. So when one goes up, the other will go down. Okay. Because why is that? Well, if you think about it, if you want to identify those people, these people who have diabetes as having diabetes, right? So we need to relax our conditions. So we will start making more and more past predictions. And if you make more and more past predictions, right? So the model, this column value will increase. So, okay. So some of them will be correct and some of them will be wrong. So both this, the 63 will start going up and this 151 will also start going up. So when that happens, if you think about it, the we will have a shift from here to here. So the recall will go up because this 151 will go up. This will not change. So the recall will be going up, but then this will start decreasing because both the error will start going up and some of the accurate predictions will go up as well. But overall, um, in general, the precision will start going down. Okay, it's not like a one-to-one thing, but that will happen. Anyway, again, some extra information there. I hope precision recall is clear because these are more important in comparing models. I would not use classification accuracy in comparing. Precision recall is more important. F1 is the harmonic average of precision recall. So it's like 2 times precision times recall divided by precision plus recall. So you can just think of it like an average between the two. And if you pay attention to the value, right, it's kind of in between these two. It's not the arithmetic average, but still it's kind of in between. So you can just think of it like the average of these two. So if you do not prefer recall or precision, you can just use F1. That's the purpose of F1. It's like like a balance between those two. Okay. And you can compare models with this. So we will soon add more models and we will see, this table being populated. So we will be able to compare the different model performances with each other. Okay, so I also had like a PowerPoint slide here. I just want to quickly show you how this looks like without, I already explained this, but you see, I put an example here. I show which, where's the true positive, where's the false positive, the negatives, etc. So here I assume class 1 as the positive class and class 0 as the negative class. And so if these are the predicted values, then based on these formulas, and these are the precision recall F1 score formulas, you can calculate both recall and precision. The way I just explained, actually, it's also kind of put more mathematically over here, that's it. And then, you can calculate the accuracy, misclassification, precision, recall F1 scores from this confusion matrix table. So I try to show them here too. So that's the F1 score right there, precision, recall, the error, and the accuracy of the model. So one example and another example. So here, this is the final thing I want to mention. The reason we should not rely on accuracy, but rather on F1 score or precision recall is especially when the dataset is imbalanced. You see here we have 88 points from the negative class and we have 12 points from the positive class. So that means even if the model didn't learn anything from the data and it was super lazy, even if it went with just a larger class, in this case 88 points negative, and it were to predict everything as negative, it will get 88% accuracy, right? So here it actually tried to do some things and it only was able to correctly identify 85, so it went down to 85% accuracy actually. So if it weren't to do anything and just go with the larger class always, predicting always the negative class, it would get 0.88. 88% accuracy without doing anything, that's pretty good. So, but so that's why, but you will know if it always predicts negative class, that's not a good model. Probably here the passive class is the important one because it's a lesser class, so probably we really want to identify those things in the passive class. Maybe it's a disease or something. So that's why we should not rely on accuracy. So here, if you were to calculate recall precision, let's look at recall. Out of the passive points, there's 12 of them. How many of them are correctly identified? 2 of them. So 2 over 12 is a recall, which is 0.17. Precision is out of the passive predictions, which is 7, right? These 7 points. How many of them are correct? 2 of them are correctly identified as positive. So 2 over 7, that's this precision. F1 is the kind of in between these two that, you can apply this formula, you will get it between these two. And you see all these 3 values are very small. Especially recall is terrible. 0.17, it's 1/5 of accuracy. Okay. If you were to just use the accuracy in this model and you would be happy because it's 85 is a quite good number, you would be very misled. So that's why, either precision recall or F1 score in general. As I said, if you don't have any specific choice in terms of the classes, just go with F1 is good enough. So F1 is a much better measure here, okay, especially in imbalanced classes like this. And that's the importance of both looking at the confusion metrics, seeing these numbers, and also looking at these confusion matrix, and also looking at this performance metrics. Okay. All right, I hope that helps. So based on that, now we can understand what these values are. AUC is area under the curve. MCC is Matthews correlation coefficient. Um, yeah, so these are also general metrics, performance metrics about the models. Um, and they could also be used, especially AUC is also a nice measure, could be used as well. It's a probabilistic measure, so that's you can also look into that. But for in general, in machine learning, um, F1 precision recall are the king, especially the F1 score. So if you didn't know anything, just use the F1 score, or for example, to make comparisons between different models. I do not want to go into details of AUC MCC because it will be um, it will take long right now, and it will be um, kind of, we don't really need to go into much detail, but so that's why I might maybe make another video about that later on. All of these metrics, they are about how good the model is. Okay, so the higher they are, the better they are. Okay, so like accuracy, AUC, F1 precision recall, the closer they are to 1, the better the model is. And the closer they are to 0, the worse the model is, because these are all about score, how good the model is. So the higher they are, the better they are. Okay then. MC I don't recall MCC myself very well right now, so MCC, the way it works might be a bit different, as I said. Um, for me, I don't really much use MCC. I generally just go with F1 or recall, depending on the situation. Generally, just the F1 really. Um, okay, so F1 is the king, I would say. Now let's add some other models and then compare them, and then we'll conclude there. So three decision tree model can be used for classification. Random forest is a combination of many trees. Um, so it's basically like at the end it will take the average of those trees, so it can be used for classification. Gradient boosting will try to improve on the previous tree's errors, so to get better trees, so it can be used for classification. KNN, it will look at the k nearest neighbors, and then it will go with the majority vote there, meaning let's say if you're looking at 5 nearest neighbors, 3 of them are class red, 2 of them are class blue. We'll go with class red because 3 of them are class red, right? It goes with the majority classification there. So all these like these forest models also, I mean, where there's multiple decision trees, they will go with the majority vote there, depending on how the trees vote. With some extra details in gradient boosting. There's also ADA boost, which is also another boosting type model. Let me put that as well here. So you see, it's this thing is so nice because you can pretty much just put the models and connect them, and this should work. So okay, let me put that here. So here now we should be able to see this table with all the classification accuracy F1 precision recall values. If you click on F1, it should sort from large to small. So gradient boosting seems to be doing very well. 0.66, recall 0.63. That's pretty good. That's much better than you see logistic regression at 0.56. Logistic regression, by the way, is a simpler classification model. It still does very well compared to these guys. Now, for example, KNN did not good, right? 0.34 for recall. So all of these models have their hyperparameters, so we can check how they look like and change some of them. So yeah, number of neighbors, I'm using now 2. Let me make that 5. So that's why you can include several KNN models here and then try different values for them, right? So to see how they look like. Okay, recall did improve. So for example, you can add like this. So, and then to keep score of it, so I will say KNN underscore 5. And this one I will try a larger value now. So I will say let's make it 10 for the nearest neighbor value. And then right click, rename KNN underscore 10. All right, let's look at it now. Recall. So is 10 better, 5 better? Okay, so 5 is slightly better than the 10 nearest neighbors there, as you can see. Based on the recall value, let me sort based on the F1. Oh, based on F1 score, the 10 nearest neighbor does, here, sorry, does better actually. So if you want to go with F1, KNN 10 looks to be a better solution there. And as I said, all these models have their hyperparameters. I will not go into details of those, but for example, if you get like a random forest, you see number of trees. There is 10 trees being created, so that means, this decision tree is a single tree. So there's 10 of them here in this random forest. I can create 100 of them. So generally, if you increase that number, it should do better. If you go way over the limit, like meaning if you go with really too many, then it can overfit. So you need to be careful on that. So let me go with F1 scoring here. Okay, random forest is now 75. Sorry, keep looking at this accuracy. F1 63, right? So what was it before? I don't remember. Let's do 10 again. Let's see the score. Okay, random forest. Yeah, you see there's 61. It was 63. So 10 trees, 61 F1 score, and with 100 trees, it's getting 63.63. So as expected, the more trees there are, the better it is. Of course, there's a limit to it. After a while, it will fade off, and it will not get any better. If anything, it might get even worse actually. But these are all hyperparameters, and you can try them and then see how they impact the model results. Okay. Um, okay then. So this is in short how you can do classification in Orange data mining and how you can, what the F1 precision recall means and how you can compare these models with each other. I'm wondering if I do random sampling, is it still gradient boosting or, okay, still gradient boosting is still in there. So I think, yeah, gradient boosting is generally a good model to go with. So we learned those metrics to compare, and of course, one of the most important things in classification is looking at the confusion matrix, what it means, how it can be used, and the importance of these values, right? So we looked at all these things. Now, this predictions, now we'll all have predictions from all of these as well. So it's very, you see, there's a lot more here now. What you see here, though, is like you will see a prediction for the logistic regression model. You'll see all the predictions from the decision tree, the random forest, gradient boosting, KNN with the 5 neighbors, KNN with the 10 neighbors, the ADA boost model. Um, and that's it. Those are all the label predictions, and then it goes into more details. Like, for example, logistic regression is making non-diabetic predictions and diabetic predictions, right? So it will show them. And then it goes to the tree. Tree will also make probabilistic predictions. So this is for the non-diabetic class and diabetic class. Random forest has the same idea, and so on. So all of these models are pretty much will give you a result for both classes in terms of probability values, and then it will predict the label to be the larger probability class. This SVM is also another classification model. Let's connect that too. Let's see how that one looks like. Not bad, it's in the middle. Gradient boosting is still a winner. Um, yeah, this one even has more. I mean, each of these models have at least several different hyperparameters that can be played with. So that's another challenge in its own way. Okay, trying to find that good combination of parameters. Okay. All right, guys. Well, thank you very much. And yeah, this is how you do classification in Orange data mining. Thank you and see you next time then. Bye.